So let me remind you what we did yesterday. So yesterday, first I introduced Calabi-Yau pairs. And we saw that there is a volume-preserving Sarkisov program. So I explained those tools, and then with this, we studied the composition group of a quartic with Picard rank 1. So we show that for S, smooth quartic with Picard rank 1, the decomposition group, so this is the group of Cremona transformation that stabilize the quartic, is trivial. So this is what we did yesterday, and then today I want to study the decomposition group, or actually I just want to maybe study general Gizatullin's problem for quartics, smooth quartics, with Picard rank 2. And then we want to understand which automorphisms of such quartics are induced by Cremona transformations. So as I said, the first thing that we have to do is to understand the automorphism group of a quartic with a Picard rank 2. So this is, okay, maybe section 3. Which is K3 surfaces. So this is just a review, or we'll introduce some of the main results about K3 surfaces that we need in order to understand this automorphism group. So let me start by recalling the definition of a K3 surface. So at least for today, a K3 surface, as I said, well, as before, as yesterday, we will always be working over the complex numbers. So a K3 surface is a smooth projective surface S with irregularity 0 and canonical class trivial, and trivial canonical class. So this means that if I look at the global two forms on S, this is just generated by a single form, a single two form. Sorry if my two W's look, well, they look the same, but okay. I don't know how to make them different. Okay, this is omega. This is the form that generates. So this is a nowhere vanishing two form that generates this cohomology group. Okay, so this is a K3 surface, and now I want to explain that there are some very natural lattices that are associated to a K3 surface. So let me introduce them. So a lattice for me is just a free Z, finitely generated free Z module together with a non-degenerate quadratic form. So lattices of a K3 surface. So the first lattice, natural lattice that we will consider is the given by the second cohomology group over Z. Together, so this is the free Z module, and then the quadratic form that we consider here is the one induced by cup product. So here together with the cup product. So this is a very well-known lattice, so it does not depend on the surface. It's always, so as a Z module, this is isomorphic to Z 22, so it's a lattice of rank 22, and it's actually a very well-known lattice, and it's the same for any S. Okay, so, and also now more algebraically, we can consider the Picard lattice. So we have the Picard group of S, which is a finitely generated Z module, and together with the intersection form, intersection product of curves. And now this one, the rank of this one will, in general, vary. So here, actually, I should say that for some people, a K3 surface may be non-algebraic, but here, for me, a K3 surface is always algebraic. So this could be 0 if you consider more general definition. And this Picard, the Picard lattice can be naturally, if you take the first Chern class, it can be naturally embedded in this one we usually call the K3 lattice. And, and inside of the K3 lattice, it can be defined as the set of vectors H2SC that intersect this unique one form in 0. And so this is a sublattice of the K3 lattice. And we can also consider another lattice, which is just the orthogonal complement of the Picard lattice inside the K3 lattice. So this is what we usually call the transcendental lattice of the K3. So this is just the peak as perp. So this is called the transcendental lattice. Okay, so these are some of the lattices that we will study. And let me see what else I want to say. Okay, so this is actually, it's a little bit more than just a lattice in the sense that if I take now complex coefficients, so if I tensor it with C, this vector space admits a Hodge decomposition, so it can be written as the notation that I'm using here. Okay, so let me just write it this way. H20 plus H11 plus H02. So this is just the Hodge decomposition. And this will be important very soon, but maybe I don't want to say anything about this now. I think this is, okay, maybe there is one thing I want to say about the Picard lattice. So remark, maybe let me put it as a remark. So the Picard lattice, by the Hodge index theorem, the Picard lattice has signature 1, rho minus 1, where rho is the Picard number. And it's actually an even lattice of signature. One rho minus 1. And even here means that the square of every element is an even integer. And there is a converse, a partial converse to this remark. So this is a theorem of Morrison that says that conversely, if you start with an even lattice of the correct signature, with small enough rank, then this can be realized as the Picard lattice of a K3 surface. So this is a theorem of Morrison. From 84, that says that conversely, if you have L, some even lattice of signature 1, rho minus 1, for some rho at most 10. Then there is a K3 surface with this Picard lattice. Then there exists a K3 surface S such that the Picard lattice of S is isomorphic to, it's, well, isometric, in fact, to L. Okay, in fact, I don't want to state this, but you even have a moduli space of such K3 surfaces together with this identification. And I don't want to state it precisely, but just because soon I will start saying for a general K3 surface, so what I mean by that is that a general in this moduli space. Okay, so now these are the lattices. Now I want to explain how we can use lattices and lattices isometries to understand automorphism groups of the K3 surface. So let me discuss a little bit automorphisms of K3 surfaces. Okay, so let's assume that I start with the S K3 surface and G some automorphism of S. Then this G will naturally act on these Picard lattices by isometry. So you get what we call a G star, which is an isometry, say, of the K3 lattice. And the same thing for the Picard lattice. So by this notation, I mean that it acts as an isometry of this lattice. But it's not only any isometry, it's an isometry that preserves, if I tensored with a C, it preserves the Hodge structure. So this it's an isometry that preserves G star preserves the Hodge decomposition. So this is what we call a Hodge isometry. And now we want to understand, so let me state this as a Corelli theorem. So let me see if I want to introduce something else before I state it. I think I'm okay. Okay, so let me state what I will refer to as Corelli theorem. And it will be, okay, I will state several statements, and then for me, just for simplicity, I'll call them this whole package Corelli theorem. But okay, the main what is really the Corelli theorem is a statement that says that this correspondence that associates to an automorphism the Hodge isometry is injective. So if you understand the Hodge isometry, then this is enough to completely determine the automorphism. So this is a good thing. But now we also want to understand now which Hodge isometries they actually come from automorphisms, and this is okay. This is well known. This is so a Hodge isometry. So if you start with a Hodge isometry phi is induced by an automorphism if and only if it preserves an ample class. So if and only if phi sends some ample class to an ample class. So, yeah, so it will preserve the ample cone. Yeah, but what I'm trying to say here is that you just have to check it in one class, in one ample class. Yes, this is equivalent to saying that it sends the ample cone to the ample cone. Okay, so this is good. We can understand how now from the Hodge isometries we can completely understand the automorphism group. But in our case, we want to do this starting not with the Hodge isometries, but we want to start it with the Picard lattice. So if you have, now we want to understand, given, okay, maybe let me put it this way. We want to understand that given given some isometry of the Picard lattice, we want to understand when can we extend it to an isometry of the whole K3 lattice. So when can it be extended to an isometry of the Picard lattice, of the K3 lattice? And again, as we will see that this is actually a very simple condition. So first of all, before I answer this, so what we know so far is that the K3 lattice can be written as a direct sum of the Picard lattice plus the transcendental lattice. Now let's assume that we start with a Hodge isometry here. So if we start with a Hodge isometry here, this will preserve this direct sum decomposition. So this is the Hodge conjecture. And so it will induce, so if I start with an isometry of the whole K3 lattice, it will induce an isometry of the Picard lattice and an isometry of the transcendental lattice. So now, if we want to answer this question, now we're starting with an isometry. Sorry, here maybe I should say O. I have an isometry here. So if I start now with an isometry, Phi1 here, of the Picard lattice, I want to extend, so I want to know when I can, I want to study now the isometries, how I relate these two isometries. So maybe I should, okay. I think I'm making things more complicated than they should be. But what I want to say is that if you start with an isometry of the K3 lattice, you get these two isometries of these two pieces, and they satisfy some compatibility conditions. So to discuss this compatibility condition, I need to introduce another object, which is the discriminant group of these lattices. So if in fact, I can define this for any lattice. So if I have the discriminant group of a lattice, so in the case of a Picard lattice, I can define the dual Picard lattice as just so I take the elements X in peak as tensored with Q. I take the elements whose pairs with any element of peak is still an integer, so such that for every Y in peak S, X dot Y is an integer. So this is the dual lattice, and in general, this is a bigger lattice, but it contains for sure the Picard lattice. And we can define the discriminant group, let me call it A of S, to be just this quotient. So this is a finite group. And it turns out that if I can do the same thing for the transcendental lattice, and it turns out that there is a natural identification of these finite groups. The dual lattice of this quotient of the dual lattice of S and the peak of T. So now the condition that I can starting with isometries of the two pieces, I can glue them to a global isometry, is precisely that when I consider the action of the isometries on these quotients, they coincide. So let me write this. So if I start with isometries of the Picard lattice, and the transcendental lattice, if they are such that the induced action on the discriminants coincide, under this natural identification, then they can glue to a global isometry. Then there is global isometry, and in fact it will be a Hodge isometry, is a Hodge isometry. Phi. That restricts to the given isometries. That phi restricted to peak is phi 1, and phi restricted to TS is phi 2. So what I want to say here is that now, suppose that we are in the situation that we understand we have a Picard lattice of a certain K3 surface, and we understand all its isometries. So for each of these isometries, we can look at the induced action here. So first of all, from the peak, we can construct the transcendental lattice as the perp. And so we can start with our isometry on peak. We see how it acts here. And then we see if we can define an isometry of T for which these actions coincide. And if you can do this, then actually this comes from an automorphism of the K3 surface. So maybe the upshot here is that, and let me just summarize it in this way. So in principle, we can, given an isometry of the Picard lattice, we can check if this can extend, if it comes from an automorphism of S. So as a consequence, maybe of all this Torelli stuff, is that first, given an isometry of the Picard lattice, we can determine whether can determine when it comes, if it comes from, if phi is the induced by an automorphism, but it can be induced by more than one automorphism, because here we may be able to define different isometries of the transcendental lattice that for which the actions agree in the discriminant. But it turns out that an automorphism G is completely determined by its action in the Picard lattice, and its action on the true form, the non-vanishing true form omega s. So here there is a, this does not follow from what I told you, but this is still true, that basically once you know the action on peak and how it acts on omega s, there is a unique way to define the action on the transcendental lattice so that it glues. Okay, and this action is always a multiplication by some root of unity. But I guess we won't need that. Any questions so far? Okay, so I guess this is in general for any K3 surface. Now I want to restrict to K3 surfaces with Picard rank 2. So in this case, the Picard lattice of such K3 surface as, so it has rank 2, so it is always generated. In fact, maybe I want to, let me already look at quartics. I could do more generally, but let me just, let me already restrict to quartics, which is what we want. So if I take S in P3, a smooth quartic with Picard rank 2, well, then the Picard group can be generated by the hyperplane class in P3. So this H, I will always denote a hyperplane class. And the class of some other curve C. So with this basis, I can write the intersection form. I will always write it in terms of a matrix. So this matrix will be, so H squared, C times H, C times H, and C squared. So this is when I write a matrix for a Picard rank 2 K3 surface, I always mean this intersection matrix. So in the case of a quartic, this is 4. This is going to be some integer b, the intersection of C and H. C could be any class. But if C is actually a curve, then I know more. I know that C square, if C is a curve, so let me write this as a smooth, so let's say a smooth curve. I can always take it to be a smooth curve. Then this is just, the C square is just 2 times the genus minus 2. So this is always an even number, so this way. So conversely, if I start with any matrix with signature 1, 1 that is even like this comes from, by Morrison's theorem, this comes from a K3 surface. It may not be a quartic. So to check that it's a quartic, you have to check that you have an MPO class with self-intersection 4. But again, this is something that you can do when if you know the lattice, you can figure it out if you can find if you can find such an MPO class or not. Okay, so this is going to be the Picard lattice of such a quartic, and now from this theory that I outlined here, one can completely understand the automorphism. If you give me such matrix, 2 by 2 matrix, I can tell you what is the automorphism group of such quartic. And so let me just state this as the theorem. Or proposition. So this, I'm putting together results of Galuzzi, Lombardo, and Peters, together with results of Paiva and Kedo. And basically, this tells you what are all the possibilities for the automorphism group of such quartic. So this is one of the following. It could be trivial. It can be Z mod 2. It can be Z. Or it can be the free product of Z2 and Z2. At least for, okay, let me say, for a general such quartic, so for a general S, you have these possibilities. And now, how do you tell them apart? So, first of all, if you want to decide whether it is finite or not, this will be finite if and only if there exists some curve or some class in peak such that C square is either minus 2 or 0. So that is, if I can find either a rational curve or an elliptic curve inside my K3, then it will be, the automorphism group is finite. And it is either trivial or Z2. If there is no such C, then the automorphism group is infinite, and it will be one of these two. And now, to tell those apart, well, you have to see if you can find an involution in the automorphism group. And then to find an involution, so to be in this case or in this case, this is equivalent to the existence of an ample class with square 2. So see, what I'm telling you here is that if you know the Picard lattice, just by looking for certain integers that are realized by the quadratic, that can be realized by the quadratic form, you determine the automorphism group. And so now we need to understand how do we, starting with the lattice, how do we determine the existence of elements whose square are some given number. And this the open, okay. So let me see if I still have it on the board. Yes, here. So I told you that the automorphism group is determined by the action on peak and the action on the form, on the true form. The action on the true form is always multiplication by a root of unity. And for a general S, this is always multiplication by plus or minus 1. So this is the condition that I want. Otherwise, what I get is that these groups are subgroups of the automorphism group of finite index. So these are always inside the automorphism group, but maybe with a non-trivial finite index. But for a general S, then this is exactly the automorphism. Okay, so now I want to explain how we check the existence of such classes. And for that, I need to define an invariant of the K3 surface, which is we call the discriminant. We also call it the discriminant, so the definition. So let S be as above. So let me just say K3 surface. This can be defined more generally, a K3 surface with Picard rank 2 rho x equals 2. Oh, let me actually write the peak. I hope this is going to be okay that I just write it this way. So maybe write it this way. So this I'm already thinking of a quartic. So this is the intersection matrix of the Picard lattice. And I define the discriminant of S is just minus the determinant of the matrix. Calling this Q. So this is B2 minus 8. So this is just a number that I associate to my K3. The reason that I put this minus here is that this will always be positive, and this is the Hodge index theorem. So this is a positive integer, and moreover, just from this, we see that R has to be congruent to a square, mod 8. And so this is congruent to B2 mod 8. And therefore, it has to be either 0, 1, or 4, or 8. This all like this. Not 8. And why is this number important? So first of all, if you give me a allowed R, a discriminant satisfying a positive number satisfying this condition, then it is the discriminant of a unique lattice of this type. So it completely determines up to isometry the lattice. And this number carries information about which curves are contained in the K3 surface. So let me state this. So this is what is going to be important about this number. that if you want to check if there exists a D in peak such that D square is equal to, say, some number k, this is equivalent to checking if the Pell equation x squared minus r y squared equals to 4k. This equation has integer solutions. And so, see, now if you give me a discriminant, I can use this to check if it has curves with square -2, 2, and 0. And so I can completely determine the automorphism group. Okay, so this is just to tell you that if you give me the Picard lattice, or if you give me actually just the discriminant, I can tell you what are all the curves that are contained in my surface. Sorry? Yes, so this is what we call a Pell equation. All right, so any questions so far? So this was, okay, this is, unfortunately, I needed to state all this so that I can, sorry, I needed to do this so that I can state the main theorem. So now, last section is the main theorem today, which is the solution of Gizatullin's problem in the case of Picard rank 2. So theorem. And so this is together with Daniela and Socrates. So now suppose that S is a quartic surface with Picard rank 2 and discriminant R. Well, okay, so first we want to understand whether the automorphisms of S come from Cremona transformations of P3. So the first part of the theorem gives you a negative answer. So if the discriminant is either greater than 57 or it is 52, then the decomposition group is trivial. So in particular, no automorphism of S can come from a Cremona transformation. And then you can find infinitely many R's for which the automorphisms are any of those. Okay, and then the second part is a positive answer. Now, if, however, R is less or equal than 57 and different than 52, then maybe here, for S general in the moduli space of surface of quartics with this Picard lattice, then every automorphism is induced by a Cremona transformation. So now here then. every automorphism of S is induced by a Cremona transformation. And here, there are few, so you see that there are few possible discriminants. And then for each of one, you can check what is the automorphism group. And in the allowed values of R, we get 2 cases here, 2 cases with automorphism group Z mod 2, 2 cases here, 4 cases here, and then the rest is trivial. And now let me at least give you an idea of the proof. Probably I won't give you too much detail, so the idea of proof. Okay, so we assume that we have a non-trivial element in the decomposition group. So this is for the first part. So let's assume that we have a non-trivial element here, and let me remind you that we saw yesterday that the decomposition group is the same as the group of volume-preserving Cremona transformations for this Calabi-Yau pair. And for this group, we have the volume-preserving Sarkisov program, and so we can consider a factorization of phi in terms of volume-preserving Sarkisov links. So let me just sketch this. So we have here is our Mori-fibered Calabi-Yau pair. And then we will have a certain Sarkisov, volume-preserving Sarkisov decomposition that eventually goes back to P3. Okay, so all of these are volume-preserving Sarkisov links. And so what we will do is let's analyze the first link. So what we have seen yesterday is that because our surface is smooth, the first link must start with the blow-up of a curve contained in S. So this is something that we saw yesterday. So first link starts with the blow-up of a curve P contained in S. And moreover, we saw also that this curve cannot be a complete intersection. So C cannot be of the form S intersection T. Okay, so now we have to look for this curve inside of S. And there are 2 possibilities here. So first, maybe I should say, in other words, let me just define X to be the blow-up of P3 along C. So to say that this starts a Sarkisov link is the same thing to say that this is a over spec K, this is a rank 2 fibration. And in particular, we saw that this requires that the anticanonical class is big. Now, just from this, you can show, just from this condition here, you can show that that C square must be less than 16. Okay? This is just a simple computation from this condition, and this is just the blow up of a curve. You can check this. And this actually is enough, because see, once you have a curve, I'm telling you that you have a curve inside of X of degree less than 16, and this curve is not a complete intersection. So if I take the sublattice of the Picard lattice generated by the hyperplane class and C, so this is contained in Pic, and therefore the discriminant of our lattice must divide, so the discriminant of the lattice must divide the discriminant of the sublattice. And now you can, it's easy to check that, okay, so this is the hyperplane class, and this is a curve of degree at most 16. So you can check that this already forces our R to be less or equal than where am I? Okay, this is less or equal than 233. And the reason why I'm stating this is that I mentioned that this was part of this theorem was proved by Paiva and S. So what they proved was in their first paper was this one, that if the discriminant is bigger than this, then the decomposition group is trivial. So this you get just from here. But now to get a complete solution, we have to go a bit further. So let me see how much time I have. Okay. Okay, so but now we will do a deeper analysis of this curve C. Now, be a bit quick here. So there are two possibilities for C. Okay, either C is such that the anticanonical class is nef. So in this case, X is weak funnel. So that is minus Kx is nef and big. Or the anticanonical class is not nef, and then the link will continue with an anti-flip. So in this case, there will be a rational curve L. There is a L inside of X, such that L is a rational curve, and it will have negative degree with minus K. But this is the same thing as just S tilde dot L. So in this case here, we see that this curve here is contained in S tilde. Well, I am identifying S tilde with S, so they're the same under the blow up. So we have to find a rational curve contained in S and satisfying this condition, okay? But okay, then here, maybe here I will be a little bit quick, that in fact, we know that more is true. We can show, okay, this is not an easy computation, but it can be done. We can actually show that the anticanonical degree of L must be precisely minus 1. And this is because if it is smaller than minus 1, when you perform the anti-flip, you get something with worse than terminal singularities. So this condition here guarantees that the anti-flip will have terminal singularities. And now you want to find, in your surface, you want to find a rational curve. So there are two curves involved. There is the curve that you blew up, the C that you blew up, and then there is also this rational curve satisfying this condition. So you write this in terms of a linear system, and then you try to solve it, in terms of you have the Picard lattice, because you're given the discriminant, and then you check that this cannot occur. Okay, this is not quite true. It could occur in one case with discriminant 9, and then actually we do perform. There is such curve for discriminant 9. You can find such curve, but then actually we explicitly perform the anti-flip, and it's worse than terminal singularity. So there is some computations here, but this is okay. Maybe I put 3 dots here. But the conclusion is that this cannot occur. So case B cannot occur. So A and B cannot occur. And so we are in case A. But here, we are lucky that we have the work of Blanc-Lamy that classify all the curves in terms of degree and genus, all the curves in P3 for which the blow up is weak funnel. So this is so this implies, so case A, we have case A, and this is, well, maybe I don't want to write this whole curve, so, but let me, so this is saying that the genus and the degree is a finite list, so let me call it BL for a Blanc-Lamy list, a finite list of possible genus. This is Blanc-Lamy. And in this list, we can check which ones actually give you a rank 2 fibration. So not all of them give you rank 2 fibrations. For some of them, when you perform some MMPs, you get to something worse than terminal singularities. But in any case, we can see precisely what are the pairs of degree and genus. Okay? So let me just write how this list starts and ends. So this list starts with 0, 1, 0, 2, so on, and then it ends with 11, 10, 14, 11, and that's it. And then now what we have to do is the following. Now we will do the same thing that we did here. You consider the sublattice generated by H and C. And then we can compute the discriminant. So the discriminant is given in terms of the degree and the genus of the curve. And so if we computed, let me call this R prime, so this is the discriminant of the sublattice generated by H and C. So the R prime in this case, so then we compute basically for each one of them. So for this one is 9, for this one is 12, and so on. And then what we have is that our R must divide R prime. But R prime, we can compute the list. The biggest one that appears here is 57. And so this is exactly tells us that, this is what tells us that R is less or equal than 57 and different than 52. So this proves the first part. And let me just briefly say how, okay, so I'll just say what we do for the second part. So for the second part now, for each of the discriminants in this list, first thing we do is we describe the automorphism group explicitly. We describe their generators as isometries of the Picard lattice. So we write down exactly, so we have the Picard lattice, and we write down for the generators of the automorphism group, what is the isometry. Okay, so this is explicit, and then what we want to do now is to realize each one of them as a Cremona transformation. So what we do is that we know that if you know, they will have a Sarkisov decomposition like this, so we just perform the links that we know. So we choose for each R, we check all the Blanc-Lamy curves that are contained in our surface. And then, okay, maybe we have to look and then choose a nice one. So many of them already give you a link to P3, and then we just find the link that we want. So we construct, using the curves, the Blanc-Lamy curves that are inside the surface, we are able to construct compositions of Sarkisov links that induce each one of the generators. So I'm sorry that I will not have time to do that in detail, and I would like to stop here. Thank you. Thank you. I will need 5 minutes, but I'm glad that you asked me this question. So now we don't know, we have not computed the inertia group. I think this is a very interesting problem, but we can already see that they can be very complicated. I mean, there is stuff there, and let me just show you an example of that. And for that, I have to tell you a little bit of the proof of part 2. So that's why I thank you for the question. Let me just give you maybe one example here. So this is the case R equals to 56. So the lattice is, we can take it to be this one here. And then from this, we see, okay, so you see that from this 2 here, we have involutions. And you actually check that there are no rational curves and no elliptic curves. So actually, the automorphism group is given by, Z2 free product of Z2. And we can write down the generators here. So at least the action, so if we write this in terms of sigma 1, sigma 2, well, we write the action in the automorphism group. So let me just write one of them. One of them is this. This is the simplest one, 0. This is an one of the involutions that generate the isometry group of this lattice. Okay. So this one here. To realize this one, what do? We take a curve, so we look inside of S, we look at a curve of genus and degree. So we have a curve of genus and degree. In this case, it is 2,8, I think, 2,8. And if I take such curve and I blow it up and do the link, so this link was studied by Zikas. It's a very nice link because it already gives you an involution of P3. So you start with P3, you blow up the curve, and then you do a flop, and then I contract the curve. So this gives me, this is a birational involution, and it preserves the surface. It's a miracle, but it happens. So it induces an isomorphism of the surface. And this is the link that restricts to this involution. So if I restrict it to S, it gives me sigma 1. But see, to perform this link, I just need to choose one curve with genus and degree. But if you look at the linear system of C, this will have dimension, let me see, I always get this one. This will have dimension 1, so this is a P1. And so what this is telling me, I can choose any curve in this linear system to induce my this generator. So if I take one curve and then if I take 2 curves and compose, then I get the identity. So we already see that you have many things inside the inertia group. So for most of the cases, we could already see that in all the cases that we realized, you could actually see that there are many different ways. I mean, you have choices to realize the link. And that means that you will have some non-trivial stuff in the inertia group. But we have not computed it. Yeah. It's uncountable. It usually has some positive dimensional stuff inside. No, but you can take it smooth. Yeah. But okay, but then we show that in this case you can choose it to be smooth. You mean for the part 1? Yes. Yes, it could involve a singular curve, but then okay, I have to think. We did consider this case. So, but we show that in the end, even if it is singular, it cannot happen. Yes. Yeah. I mean, okay. It's not automatic, but you have to an argument. But okay, I have to think about this a little bit. Yes. I would love to see such an example. I don't have an example, but I would love to see an example where you have something in between. You have some automorphisms that are induced and others that are not. If you find it, tell me, please. Yes. Maybe since I'm the last speaker, I would like to. I invite all of you to thank the organizers, and especially Michelle, for organizing this very nice school. Thank you.
Then the open set is there are divisors with their countable numbers. Each divisor you have to fix
General.
their